Up until now, we have dealt with prediction intervals. So what's a prediction interval? It's really the prediction that you get from using the regression line. So for example, you have the regression line here with x and y, and you choose a certain x, and then you can use this line or the function, the equation that you get from the line to get a certain y hat, right? Okay, so y hat is the point estimate or point prediction from your regression line. Okay, so how do you use this? For example, what would we predict for sales at a location with 50,000 people who walk by every month? Okay, so here you just use the equation with the intercept plus the slope times a certain x nu. Okay, so your best guess in this case, in the Bucket-Hansen case, is taking the intercept 133.81 measured in thousands of kroners plus the slope of 23.67 measured in thousands of kroners per thousands of pedestrians, right? Times 50,000 pedestrians, which equals 1,049.69, which is the sales as measured in thousands of kroners. Okay, so this is really just 1.050 million kroners, right? But the question is, now you have this point estimate, but most probably sales will not be exactly lying on your regression line. So could sales be as low as 500,000 kroners or as high as 2 million kroners? And how accurate would your prediction be? Because if you look at the regression line, let's see how far back we have to go. Yeah, here we get it. Here we have the regression line, and our new x nu is 50,000 pedestrians, right? So you go up here, and the regression line gives you the new estimate. But you see that there is kind of a variation around the regression line, which is not possible to explain by the regression line itself. So how can we make a certain band around the regression line, like a forecast probability around the regression line, to say something about the certainty of our prediction? So then we go back to our slide, and we are going to make a prediction interval around the point estimate. Okay, so a prediction interval is an interval designed to hold a fraction usually 95% of the values of the response y for a given value of x. So what I like to draw is this vertical line to have the y hat in the middle, because the prediction interval is symmetric, and we're going to talk about that during the next slide. And what you do is that you go up from your point estimate by sorry, by this critical value. So if you want the 95% prediction interval, then you have to choose a t-value to go up, a critical value which should contain 2.5% of, or be the cutoff between a tail probability of 2.5% in each tail. So if you say that well, 2.5% of the predictions, the actual values will lie outside of my prediction on either side. So that's why you choose the critical t-value, which will do that, give you 2.5% in each tail. So then you go up by this critical t-value, which is the number of standard errors you have to move, 0.025 and minus 2, which is the degrees of freedom, times the standard error of the point estimate itself. And of course, by symmetry, you go down by the same amount, and minus 2, which is the degrees of freedom, times the standard error of y hat. So what you do now is that you've created this band which should contain 95% of the observed values, okay? Because you are giving one estimate, a point estimate, and you're saying that, well, this is the mean of all the observed y values. But if you want to be certain to the 95% degree, then you have to make this prediction interval. Okay. But the standard error of the y hat is a function of the S of E, which is the standard deviation of the residuals, and times this square root, which makes the standard standard deviation over residuals higher, because all the terms under the square root, they are positive. So but as n goes to infinity, these terms go to 0, okay? Because the denominator increases, but everything else is constant. Then all of these go to 0, and even this goes to 0 because this is the x new, which we can maybe make a drawing of. For example, you have all these data points, and this is the average of x. And if you choose a new x new, far away from the average x, then this numerator will be quite large, and it's measured in standard deviation of x. Let's see. So this divided by this gives you the difference here as measured in standard deviation. Okay, but as long as you have a large number of observations, this ratio will be going towards 0 anyways. But if you don't have many data points, then if you choose an x new far away from the average x, in terms of standard deviations of x, then the standard error for the y hat is greater than the standard error of the residuals. But if you have quite a large amount of data points and you're not extrapolating a lot, then you can rely on the approximation of y hat plus minus 2 times the standard deviation of residuals. And the standard deviation of residuals, it's often called, well, let's see on the output from Stata, it's in Stata it's called root MSE. Okay, root mean squared error. Okay, so if you have large N and you're not extrapolating, then you can use this approximation. Okay, so a very important point is that the prediction interval differs from a confidence interval. Okay, what I like to do is to think about the prediction interval as this vertical line around the regression around y hat, and I'll just cut this. Yep, and the confidence interval they are kind of these horizontal lines where you have the beta naught and the slope, and you make kind of interval along the number line where these should be. Okay, so the prediction intervals, they are really only reliable within the range of observed data. For example, if you have data here and suddenly, let's see, and you're estimating a line, and suddenly you have an x new over here, you have a lot of white space between your data points and the new prediction, which means that your data or your regression line, it was fitted based on different data than you use for your prediction, which is quite dangerous. So, and in addition, the prediction intervals, they are sensitive to the constant variance and normality assumptions, and the reason is that if you have some data, and you have not got constant variance, you see that the variance is increasing with increasing x, and what the model is giving you is as a constant or an average residual standard deviation, right? So for example, the average standard deviation is here, or your prediction your prediction interval is here. The line in the middle is your regression line, it's y hat, and you see that for small x, you overestimate the variance in your prediction, whereas with large x you underestimate the variance in your prediction. Okay, so for example, this is the 95% confidence interval. And the normality assumption, it's quite important because you use the standard deviation of the residuals to create to say something about the probability, and the reason why you can say something about the probability of this distribution is only because it's normally distributed. Okay, if it was not normally distributed, you could not use the standard deviation of the errors to create this band, because with a non-normal distribution you would not know how much of the distribution you actually covered by using these standard errors, okay, or standard deviation of the errors. So we can look at one example, and that's Bucket Hansen. And what is the 95% prediction interval for the monthly sales of a location with foot traffic level of 50,000? Okay, so from the regression line, from the y hat equals the sample regression line, that would be your point estimate. Okay, so what is y hat in this case? We already calculated that as the intercept negative 133,081 plus the slope of 23.67 times 50,000 equals 1,040 let's see, 69 it should be, if I remember correctly, 69. And it's always a good thing to this is the X new. It's always good to actually check your prediction in the graph, okay? And we saw that a couple of slides ago that we found this. Let's see here. We looked at this graph, and if you go from X new up to the graph, and then from the graph until the sales axis, then you see that our calculations, they seem to be correct, because here is 1.05 million kroners. Okay, so if we go back to our example, then this is the point estimate, but we have to go up by 2 times the standard deviation of the errors. Then we have the 95% prediction interval. It's y hat plus minus 2 times the standard deviation of the errors, which is 1049.69 thousand kroners, plus minus 2 times the standard deviation of the errors. We found the root MSE, root mean squared error, is 150.54, which gives us a range from 749 point, let's check my numbers, until 1351.8. So with a 95% certainty, you can say that the actual value will lie within this range of about 750 and 1,350,000 kroners. So that would be 750,000 kroners till 1.35 million kroners. Okay, see you next time.